going to be talking about improvements on Johnson-Lindenstrauss. It seems to be the hot topic of the year.
Thanks. Does this work? I mean, it's good? Okay, good. So thanks for having me. I understand this is an hour talk, so I'm going to spend kind of half of it, slightly less now. I'm going to spend roughly half of it kind of surveying the history of Johnson-Lindenstrauss projections and mappings and techniques that people used and ideas. And then roughly the second half on newer stuff, but basically new results. Feel free to ask and comment and add stuff.
So you don't feel constrained to stop at the listed time of 12:15. First, there were 10 minutes of technical delays, and secondly, everybody always goes over.
Okay, good. I'll take. Thanks. Okay, don't feel bad to just get up at 12:15 and going away. I mean, it's fine. I want to also thank Emmanuel Candes for making fun of me and Nir. I was in Yahoo, and Nir just joined the Technion from Google, and Emmanuel Candes met us and made fun of everybody in Yahoo and Google that only want to sell ads. And it's like, okay, maybe we don't care only about ads. So, kind of also motivated us to work on this.
Isn't that true?
What?
That you only sell ads?
Well, it is, but it's still insulting. Okay, so let's start with a more survey-ish part of the talk. So we're interested in near isometric embeddings of points from one Euclidean space in high dimension. Here is going to be D, represented by 3 space. We want to map it into a lower dimensional space, K, there in 2, such that all the pairwise distances between points are preserved up to distortion 1 plus minus epsilon. And clearly we would like to have the target dimension be significantly smaller than the original dimension. And just to give an example, I mean, I'm going to fly through this, but just to give an example of why you would want such a thing, if you wanted to do like image comparison or search for almost duplicate images, if you had 5 megapixel images and you had like 10,000 of those, it'd be pretty hard to load all of them to memory. Let's say you wanted to do the stupidest possible thing, which would be to just subtract 2 images one from another, do all pairs, and if the distance is smaller than something, just raise a flag that it's a duplicate, then you would probably need to load all of those to memory, and that would be like 22 gigabytes. And before I joined Yahoo, I thought that was a lot. So, so now I know this is not too bad. So, but it's still not the nicest thing to do. But if you just projected every image to like 500 dimensions and compared the sketches, you could probably get away with storing everything in memory and doing everything on a laptop pretty efficiently. So that's kind of the excuse. But for everybody who does, everybody who knows this, I'll talk later. This is very useful not only for stuff like that. So for random projections, what we say is that basically, if we just choose a projection psi randomly, such that the probability of any unit length vector for being distorted by more than epsilon is smaller than 1 over n squared, then just by the union bound, I'm going to get that all pairwise distances are preserved. So just the probability of failure is small enough that I know that all the distances are going to be preserved. And in '84, Johnson-Lindenstrauss showed that if I just choose this psi matrix to be a random projection, being a k-dimensional subspace chosen uniformly at random from all k-dimensional subspaces, then the probability of distortion by more than epsilon goes exponentially is exponentially small in epsilon squared and k. And if I just want this thing to be smaller than 1 over n squared, then I get that the target dimension is log n over epsilon squared. Okay. And from this point on, we're going to say that this property is the JL property, or the Johnson-Lindenstrauss property of mappings. So we get 3, maybe 2, depending how you count, very interesting properties of these mappings. First, the target dimension is independent of the original dimension, which is maybe surprising, maybe not. I was surprised when I learned that. It's also logarithmic in n, the number of points, which again, is just very useful for algorithmic reasons, but it's also very surprising because that's kind of the lowest dimension you can probably hope for. Not probably, you can show that it's the lowest dimension you can embed points into. But also, and maybe most importantly, the mapping was chosen independently of the input. So I don't actually need to have an input in order to choose the mapping. So this makes these properties make random projections very, very useful in of course, dimensionality reduction and embedding and stuff like that. This is the obvious, straightforward application. But also in nearest neighbor algorithms, for example, when you want to project query points that you have not seen before. So you don't have the input before you choose the mapping, for example. Rank-K approximation of matrices, regression, compressed sensing, in graph specification, in many different topics. So this ends up being extremely useful. So let's first show the original Johnson-Lindenstrauss proof of why this works. Okay, so they had the very astute observation that if I just choose a k-dimensional subspace psi and apply it to a vector x, if I look at the norm of this thing, it actually, the distribution of this random variable is actually identical to another random variable, which is just take the first k standard basis vectors, like basically the identity, the k by k identity matrix, and then padded by zeros all the way to dimension d, but project on that a random vector from the sphere. Okay, so instead of taking an input fixed vector and projecting it on a random space, choose the space to be the most convenient one for you, but then choose the point randomly. Okay, which is, if you rotate the entire space, it doesn't matter the dot products.
You're assuming in your projections a rescaling?
Yeah, the projection is rescaled by some factor, just to make the, it needs to be rescaled. So this becomes just a function of unit vectors and chosen uniformly from the sphere, and you can just apply isoperimetric inequalities to this thing and show that the concentration is strong enough. But maybe you don't like isoperimetric inequalities and you think this is still a little bit complicated and you want a slightly simpler proof. So a few years later, Mahara showed that you can, instead of choosing a uniform subspace, you can just choose each entry in the matrix psi to be independent IID, like IID with distribution, with Gaussian distribution. And the proof that this is correct is actually quite simple. So you have this matrix who's filled with these IID Gaussians. You multiply it by a unit vector x. Because the Gaussian distribution is rotational invariant, this thing becomes just like a sum of independent Gaussians themselves. So the norm of such a thing just looks like a rescaled square-rooted chi-square distribution. Okay, this is just an identity. But the square root of a chi-square distribution with k degrees of freedom for k moderately big behaves, this is slightly hand-wavy, but it does behave very much like the normal with mean 1 and variance 1 over square root k. So basically, this thing concentrates around 1 with very small variance, and this, in a sense, is a one-line proof of this of this property. So,
credited Dasgupta and Gupta as an earlier.
yeah, I don't know exactly. I actually thought, I mean, after thinking about it for a while, I decided it's probably them. But yeah, it's the same thing, and it's from the same time, so I really don't know who did what first. So yeah, Gupta and Dasgupta have basically the same statement, and I don't know who's first, so they should get some credit too. You're right. Okay. Later, Aklioptas and then Matushak showed that the entries in the matrix don't have to be these Gaussians. They can actually be anything almost, except they need to be anything that's sub-Gaussian. Aklioptas showed specifically for plus minus 1 or plus 1, 0, minus 1, but Matushak showed that for any sub-Gaussian distribution this works.
So what is sub-Gaussian?
It should be dominated by some Gaussian times with some constants, both in, and the claim is very similar to before, but now we don't have the rotational invariance. Now what we have is that this matrix times the vector is basically the sum of rows of this matrix times this vector, but the dot product of a row and of the rows of this matrix and the vector are now also independent. And if this dot product also behaves like a Gaussian or a sub-Gaussian, which it does for plus minus 1s because of Hoofding, and for sub-Gaussians because of what Matushak showed, that this also behaves like something like Gaussian or sub-Gaussian, and the sum of those square behaves somewhat like a chi-square distribution, and so the same kind of thing follows. Okay. So we can have IID distributions, and we can have a very wide variety of IID distributions, but the problem with all of those is that storing these matrices requires storing the entire matrix as K times D matrix, or K times D. And mapping points mapping our points from the high dimensional to the low dimensional space requires this K times D operation. You just have to multiply by the matrix. So psi itself already takes 10 gigabytes of memory, which is, depending on who you ask, if you have a laptop, that's pretty nasty, but if you have like a server, that's not bad. But also, if you just look at the time that it takes you to do this, just count the operation. So 5 hours was my calculation on my laptop with paging and stuff like that, whatever. I mean, ignore the time here, it's not correct. But if you can load the entire matrix into memory, this is faster, but it's still not nice. It still take quite a few seconds for each mapping, which is probably unacceptable if you want to do a lot of those. So the immediate or the more I don't know, the first question that you might want to ask is, can I make this matrix sparser? Okay, can I have a distribution over sparse matrices that has the same that have the same properties, and then I will save both on space and on application time. In a series of papers which are surprisingly recent, it was answered that yes, you can sparsify these matrices somewhat, and you can get a factor epsilon less non-zeros than epsilon is your prescribed precision. You can get a factor epsilon better than just having the entire dense matrix. But there's also a negative result that says you can't improve this much. I mean, this is pretty much as you can do. And in the regime where epsilon is constant, then this is not better than naive. And if it is, it's not much better. We want to somehow be much faster than K times D. We want to be significantly faster than just applying a dense matrix. And their proof was basically that if you look at those very sparse vectors, these input vectors that look like zeros and like only 2 1s somewhere, then the length of the projection is basically, the distortion is governed by the dot product of the two corresponding columns in your projection matrix. And if the matrix is too sparse, then at least two columns are going to have a high dot product. Okay, the collisions just can't cancel each other anymore. We don't have enough degrees of freedom. And at least two columns are going to have a high dot product, and that will give you a big distortion, and then, that will give you the lower bound. Okay? So this question, so the question was, so the natural question is, what happens if your vectors are dense, or they are not in the form of these like zeros and 2 1s? They're kind of spread all over. Can you do better? And this question was answered 3 years before it was asked. So, so this is giving it in a story more than it is chronologically correct, but maybe it makes more sense that way. So first Elon and Chazelle, and then Matusha kind of cleaned it up and made it more crisp, maybe, showed that if you have input vectors whose L infinity norm is bounded by some eta, okay, so these vectors are not of the form 0 and then 1s, some small constant eta, then your matrix can be, the matrix can contain non-zero only with probability q, basically, and this q is proportional to eta squared in k. So the parameters are not very important here, but the idea that, yes, if the vectors are very spread, then you can have a pretty sparse matrix, and that will still hold. This will still have the JL property. So the algorithm that Elon and Chazelle proposed in 2006 was to make this random projection procedure a two-step process. First, you pre-process the vectors, or pre-process the points, by randomly rotating the entire space by multiplying each point by a random diagonal plus minus 1 matrix, which clearly doesn't change the norm, and then applying a Hadamard or a Fourier transform, which also clearly does not change the norms. Okay? But although this rotation is isometric, it kind of shuffles the entire space enough such that with very high probability, the L infinity norm of all your vectors are small. Basically, 1 over square root d, which is the lowest you can expect anything. This is the lowest possible in dimension d, plus, multiplied by square root k, which is hopefully not very big, so there's a big gain here. And then they say, well, after you've rotated it, you can apply the sparse matrix from before. So now all the vectors are spread. We can apply this sparse matrix, and only k cubed non-zeros in the sparse matrix are enough, and you get the JL property. Which was a breakthrough because this is the first asymptotically faster construction of a JL mapping. But in a sense, there's a drawback because it's only fast. It's only O of d log d if d log d is bigger than k cubed. Right? So somehow if k is smaller than d to the third, then this is governed by k cubed, and your mapping is not fast.
What is the Hadamard transform?
So a Hadamard transform is an orthogonal transform, which is both. So H. So there are a few ways to define it, but the easiest way maybe is to have H1 be the matrix 1, 1, 1, minus 1, and to have HK be the Kronecker product of HK minus 1 and H1. So as an example, H2 would be 1, 1, 1, minus 1, 1, 1, 1, minus 1, 1, 1, 1, minus 1, and then minus 1, minus 1, minus 1, 1. Okay, so these, what?
You want normalization?
Yeah, so it should be normalized by 1 over square root the dimension. Yeah, you can have a 1 over square root 2 here, and then it keeps on being normalized. So the nice thing about them is that they can be applied fast. You have like a fast Fourier method for this. You can apply.
Is the Fourier transform a special case of this, or vice versa?
No, it's a different transform, but it's just it's similar. Yeah.
It's Fourier
It-
over
Fourier on Z2 to the n.
It's all the parity functions, right?
Yeah, except here you're not applying it to
Okay.
Don't you have an overhead of randomness here? You do use more random bits here.
You use less random bits from the
Oh, okay.
compared to the, assuming this is smaller than the entire k times d. I mean, yeah.
So, what is K here?
So
Is it
so k is the target dimension, which is
log D?
so this is usually thought of as log n over epsilon square, which is the
I see, log n rather than. So the point is that it's comparing n to log to d, even though it's logarithmic, n might be like.
So there's a quite subtle game here with all the parameters to figure out exactly what is better in what scenario. I mean, it's kind of confusing. Maybe.
So in the example, D was rather much. D was 500. No.
D was like
K was 500.
yeah. So D was 5 million. Yeah. So.
Yeah. So in that case, the K would dominate.
In this case, the k would dominate. Yeah, 500 cube. Yeah.
I guess the other thing, k cubed has an epsilon to the 6 factor in it. So if epsilon.
Yeah, I mean, yeah. So that's horrendous. In a sense, for any application which is actual, I mean, k cubed would dominate by far in this scenario. I agree. Probably. Okay. So.
Is there some intuition as to why you do need the Hadamard transform? Because D already provides you a random rotation. Why do you have this?
D is a plus minus 1 matrix. I mean, so a plus minus 1 diagonal matrix.
Plus minus 1 diagonal.
Yeah. So it doesn't change it just flips signs. Doesn't change the infinity norm at all.
But that makes your Hadamard transform.
But exactly. So it's like yeah. I mean, it's like whatever. We can move on forward. It's just like applying a Hoofding inequality for which one of the coordinates independently. So you get something pretty small.
You need to use something random for your Hadamard. Otherwise it's
Right.
Okay.
No, but my question was why Hadamard? Can you just take
You can use any. You can use any orthogonal. Any orthogonal matrix with bounded entries.
Multiply it by fast by the.
Yeah, and you want to be able to do it fast. So any Fourier like or whatever, any one of those things. What?
And you don't need to store the matrix.
And you don't need to store the matrix. No, you just apply it. I mean, you have an algorithm for it. You don't actually store it. Okay.
One more. So you're always considering the problem of how fast does it take to project one point.
Yeah.
So there's no n really in this problem. It's just that.
Yeah. N is just a probability.
I see. And if you have n, you is
Just
best
multiply
to
it by n.
N times this, or could you do faster?
That's a good point. I don't think. Well, I haven't thought about it too much, I have to say. Intuitively, probably not. I'm.
If you use
Fast matrix.
yeah, I mean if you just use if you weren't taking advantage of the specific structure of the matrix, just we're multiplying random matrices, then you'd want to use a fast matrix multiplier.
Right, but you don't. You have this very fast construction. I mean, I doubt
the
you'll get.
matrices you're multiplying are not general. I mean, multiplying the diagonal matrix is really easy.
Yeah.
Right. I'm saying this is so, but it's
Yeah.
not clear how much this method saves over the naive choice of matrices, but with a fast matrix multiplier.
No, it does. I mean, it's logarithmic, right? So
And you don't have to store anything.
you don't have to store anything. It's logarithmic. You don't. It's not a polynomial save in the size of the matrices. It's actually much faster. And also, I have to say, I didn't think about it, especially because usually these things are used in the streaming kind of model. You assume you get one vector at a time. You don't get the entire batch. But maybe I should have thought about it more. I mean, maybe there is something to do there. OK. Wow. We're behind. OK, so the question, we wanted to remove the k cubed thing. And the question that Nir, Elon, and I asked ourselves is, what happens if instead of this sparse matrix, I just compare it, we just plug in there a carefully constructed, beautiful, like good matrix for us, that we can apply it fast, and it has some property that we can control. And we said, OK, so let's have some randomization and add this random diagonal plus minus 1 matrix in front of it, just so we have some randomization. And we asked ourselves, what conditions this A matrix needs to have so that this is a random projection? Okay. So if we just look at this A times D times X, the input vector, if we just open up the matrix multiplication, we get on this side that this is exactly identical to some matrix times a vector S of random bits. Okay? And this matrix M is just the columns of the matrix A multiplied by the corresponding values of X.
What is this? What does Rademacher refer to?
Plus minus 1 in probability 1/2 each. So from Talleyrand, we can derive this inequality, that any matrix multiplied by this random plus minus 1 vector concentrates around the Frobenius norm of the matrix M, and the concentration is strong. Concentration is exponentially small in epsilon square, and 1 over the 2 norm square of the matrix M. So this gives, I'm reminding you, this was the Johnson-Lindenstrauss property that we were going for to begin with, which is that we wanted this to be around 1 with this probability. So basically, we get the Johnson-Lindenstrauss property if the Frobenius norm of M is 1, and if this is 1 over k, if 1 over M, the spectral norm of M square is k, basically. So the spectral norm, or the spectral norm of M needs to be 1 over, so k to the minus half, basically. So if we just have these two conditions, just by Talleyrand, we have that this matrix is a random projection. And we showed two more things, that if that just the 2 norm of the matrix M is like the 2 to 4 norm of A transpose multiplied by the 4 norm of X. This is just Holder's inequality. If you open up the sums. And if you use a 4-wise independent matrix A, you get that the 2 to 4 norm is something like that. And unfortunately, we had to have now that the 4 norm of the vector X is smaller than d to the minus 4. So the way we had to do it is, again, to have these, now not one random rotation, but many, many random rotations. And we got the following thing, that if you repeat this random sign and Hadamard Fourier transform many, many times, I mean, some constant number, but a few times, then you reduce the L4 norm of the vectors to something like random CD to minus 4th. And then you can use this 4-wise independent matrix to project. And this also has the Johnson-Lindenstrauss property. But unfortunately, to build 4-wise independent matrices, they have to be of certain sizes. So we still get this barrier that now k still needs to be smaller than square root t. Instead of, we had k to the third before, and now it's k to square root d. So the constraint in k is weaker, but still there, which is very annoying. Okay. Another reason why we cannot go, why k cannot be bigger is because these rotations stop working. In a sense, the original dimension is already very close to log n. And so any union bound-ish kind of argument that you want to do doesn't give you much. It's already, the log n that already gives you trivial stuff. It doesn't give you anything, basically. So if you want to remove the constraint on k, we're in a problem. And on the one hand, this processing trick, this two-step process, is probably not going to work anymore, because we know that if the target dimension is the original dimension is very low, then this pre-processing trick stops working, basically. But on the other hand, sparse vectors, I mean, we still have this original problem that these very sparse vectors, the 0, 1, 0, 0, 1, zeros, vectors are pretty bad for us, and we get large distortions. Or we seem to get large distortions. And this is where Immanuel Candes's taunting begins. I mean, so we talked to him about compressed sensing and about this RIP property. And it seems like in compressed sensing, people have been studying these simple constructions that seem to preserve the lengths of sparse vectors naturally. And what I mean by that, they have constructions for RIP matrices, or restricted isometry property matrices, such that for any R sparse vector, they have this beautiful property that looks exactly like what we need for an almost isometric embedding. I mean, this is exactly like the Johnson-Lindenstrauss.
Question what you were saying before. I mean, earlier you used that if you get a vector with a random, basically a random Hadamard matrix, its L infinity norm becomes small.
Yeah.
Isn't that better than having a small 4 norm?
It would seem that way.
But that was the trouble, right, with the second thing, right? That you had to get your vectors to have small 4 norm.
No, so the L infinity norm is, so the L infinity norm you cannot reduce to get to 1 over square root t, which is the best it can be. You cannot. You have this logarithmic factor there that you get from a union bound. You cannot get around it. Actually, it's not even an artifact. The biggest, so think about the L infinity norm of a random vector. The L infinity norm of a random vector is actually not 1 over square root t. It's slightly bigger. Okay, it's like some square root log n bigger. If square root log 1 over the probability or whatever, something like that. But the 4 norm we could actually reduce all the way down to 1 over d to the 4th, which is the absolute minimum that you could hope for. So in a sense, randomizing the 4 norm is more efficient. Or it gets you to the absolute limit, where the L infinity norms has this gap.
So this log factor would appear in your running time?
The log factor would appear in yeah, so the log factor would kill everything, because you have to have this spectral argument, and you just won't be able to build such matrices. I mean, so we can talk about it later. It just breaks everything.
You won't have a code matrix that's good enough for
Exactly.
But the number of applications of these projections, you applied many times to have it close to.
Exactly. Yeah. Yeah.
So this number should depend on the log n, no?
So I'm hiding some hairy details. So there is some delta there that's hiding, and I mean, I'm hiding some hairy details that's really less important right now. So actually it should be less than, so there is some delta hiding, and you want to do this some 1 over delta times, and less interesting. Conceptually, this is what's happening. So this is exactly what we want. And also, there is a very simple construction. So it turns out, so Rulson and Verschainen improve on a result by Candes, Romberg, and Tau from 06, and show that if you just choose R log to the 4th d1 over epsilon square rows from a Hadamard matrix, or a Fourier matrix, and scale them appropriately, then this thing is very likely to have the RIP property, okay, which is that thing. And we thought, wow, this should be pretty useful, because first of all, this is exactly the condition that we need. Second of all, it naturally deals with all the sparse vectors. That these are exactly the ones that we thought are the hardest for us, and suddenly we get them for free. And also, it doesn't have this constraint. It doesn't have this hard limit between R and D. I mean, we don't have to have the sparsity smaller than square root the dimension. It can be kind of whatever you want, as long as this is less than the dimension. But as a side effect, we just get a very simple construction. So this is just a subsampling of a Hadamard matrix.
So what is R?
So the lemma here is that if you choose this R log to the fourth D over epsilon squared, then this is good for all R sparse vectors. So this is, I mean, we don't know R. R can be whatever you want here. So we want to somehow use this to generate random projections. What? This is a major, major open problem. Do I think so? I think so, but I think yeah, it's a major open problem that it's not even known if you can have any construction that eliminates the L to the D to the fourth, to the log to the fourth D in running time. But I mean, but for this subsampling of a Hadamard, if this is RIP for log D, this is a major, major open problem. So even reducing it from log to the fifth D to log to the fourth D was considered a pretty significant achievement. Okay, so we suggest the following construction, saying, well, so let's just choose log n. This is log to the fourth d, 1 over epsilon to the fourth now. We choose these many columns from a Hadamard matrix. And we just scale it down appropriately and multiply by a random diagonal matrix, the same trick we had before. And we claim that this has the Johnson-Lindenstrauss property now, okay? But without the constraint on k. So this works for any k smaller than d, okay? And again, as a side effect, we get that the construction is much simpler. We don't have these many rotations and then a code matrix. We just have a random sample of a Hadamard. Okay. So how do we prove this? Still have a lot of time. So how do we prove this? We have the following very simple observation. I mean, if we have our matrix times the vector, we can just sort it according to absolute value. Take the first log n over epsilon biggest entries. We'll call it x high, say. And the rest would be x low. And what we'll have intuitively is that the x high is going to be sparse. So somehow, just by the restricted isometry property, we're going to have that its length is preserved. X low is going to be L infinity bounded because it's the rth largest entry cannot be, the rth largest entry cannot be bigger than 1 over square root r, otherwise your vector is not unit length. So this is going to be dense or spread out. So somehow the random diagonal stuff is going to, could be 0. 0 is great. I mean, we don't want a large distortion.
One entry which is small, but it's relatively. You could just have one entry, right?
There?
Yeah.
Yeah, but it's still L infinity bounded. I mean, it's fine. It's still going to be small compared to the rest of the vector.
Okay. The entry is going to be small.
I mean, not necessarily small compared to x caret or whatever.
Yeah, I agree. I mean, so. Yeah, so what you can conceptually do is actually have the largest, the r plus 1th largest entry here, and then fill those up by the same value and subtract it from the highest ones. You can, but you don't have to. It just simplifies everything. Just take this and just be okay with the fact that this is actually if this is small, then this is small, it's much smaller than x high, and you just get the concentration to be strong enough, so you don't need to. So this is what we're going to go for.
So the bound of the infinity norm here is 1 by root log n. It's what this. The bound is 1 over root log n, right? 1 over square root log n.
Here?
Uh-huh.
Yeah, it's like epsilon over root log n or something. So let's go step by step. Well, if we look at the x, the distortion of x high, then we just get by the RIP property of the matrix phi that we get x high square and some additive epsilon distortion. So this was free. This was out of the box, just using Rudolphson and Verschainen's theorem. Then we have some cross products between x high and x low. But this is also pretty easy to bound by something of the order of magnitude epsilon, because if you look at the supporting bits in the matrix D of x low and the supporting bits of x high, they're disjoint. So this is actually linear in those random bits, this expression. Each one of them appears only once. So we can just use like Hofting or Chernoff or something. So something pretty simple here just gives you an epsilon bound on this thing. But we somehow also need to bound we also need to show that this matrix times x low is also concentrated around the norm of x low, which seems to be significantly harder. And the only way we manage to do this is actually going into Rudolphson-Verschainen's proof and extending it. So let's just see why we need Rudolphson-Verschainen's proof to do this. The same way we did before with the matrix A, with this BCH code thing, we use Talleyrand again, and we get that this holds true if somehow the spectral norm of this matrix is small enough. It's something like this expression over there. And by dx low, I mean a matrix holding on the diagonal the values of x low. So it's like okay. So this is some matrix, and we want to bound the spectral norm of that. And we use Talleyrand the same way that we did before. And also, of course, this square is the same. The spectral norm of this square is also, of course, the spectral norm of that times itself transpose. So this is that. And just by the triangle inequality, we can add and subtract this diagonal square matrix x dx caret or whatever, low. Yeah. Now this one, obviously, the spectral norm of this guy is exactly what we need, because we know that L infinity. So what's the spectral norm of a diagonal matrix? That's just the largest entry on the diagonal, which is small, because we made sure that the L infinity norm of x low is small. So this is that, and we get it for free. That's pretty easy. And what do we do with this? For this, we needed Rudolphson-Verschainen's proof. And basically, we extended it such that for any L infinity bounded vector z, if the L infinity is bounded by alpha, then you have that with high probability, or the expectation is enough for, on the choice of phi, which is the choice of the rows of the Hadamard matrix, then the supremum over all L infinity bounded vectors of this expression is bounded by something by alpha times log square d over square root k. This also gives as this is a strict extension of the Rudolphson-Verschainen lemma, because you can also replace, instead of L infinity bounded vector z, you can also replace sparse vectors. And the ratio between the L infinity and L2 is bounded just by virtue of them being sparse. So if you just plug into these sparse vectors, you get sparse reconstruction, or RIP property. Okay? And unfortunately, I won't have time, and it's kind of difficult to get into how we get this. But let's just say how we use it. And for us, we have these z's are the x lows. So the L infinity bound is this epsilon square over log n. Epsilon over square root log n, and so epsilon square is that. And if we just choose k, the target dimension, to be log n over log to the fourth d over epsilon to the fourth, then we get that this thing is smaller than epsilon square over log n, which is what we wanted, and this kind of concludes the proof, and gives a and shows that that this construction. Let me just go up. So and shows that this construction has the RIP property, So I basically choose this phi matrix by subsampling a Hadamard and diagonalizing and running through this again. Just to recap, what's happening here? Oh, so yeah, so the x high terms were just given to us for free from the RIP property. The cross terms were small just because of Hoofding or Chernoff or something. And then the concentration of the x low was given by this extension of the rules on Rashin and lemma. But this is somehow less satisfactory because we still have, we started with having an optimal dimension, optimal projected dimension of log n over epsilon square. And suddenly we have this log to the fourth d, which is kind of annoying, and we have this epsilon to the fourth. So this is the last slide. It turns out that if you go through this last derivation slightly more carefully with slightly different parameters, you get dependence of epsilon to the minus 3 instead of epsilon to the minus 4, which is better, but also kind of irrelevant because by the time we figured it out, Kramer and Ward showed that something stronger holds, which is if you take any RIP matrix and multiply it with a diagonal matrix, or diagonal plus minus 1 matrix, you get a random projection. And also their dependence on epsilon is the correct one, is epsilon to the minus 2. So this extends our result and improves it, but there is still this log to the fourth d. So we still have a ways to go to get to the right dimension and fast. So Nir and I think we might have a way to do it, but we are really not sure. I mean, we have no idea. We really are.
So I guess when you're actually computing the subsampling the Hadamard, you just sort of have to do the Hadamard in place and then just take some small fraction of the entries and throw the rest away, right?
No, you don't. I mean, you can actually just compute the ones you need.
Oh, yeah.
So it doesn't take space d squared? You can do it in space? Like
Yeah, you can do it in d log k operations.
also space?
Yeah. So you basically don't compute what you don't need. If you just go through the recursion and
Just that for Hadamard, you have to sort of have all the, okay.
yeah, it's if you just look at the recursion and kind of trim it in the right way, you get that it's d log k and in place, and so you. But we only care about the regime in which k and d are kind of polynomial in one another. So log d or log k is probably the same thing.
But for your original motivating problem, this presumably does this help at all?
Yeah, so this is significantly faster. I mean, right?
No,
So
for your files on your laptop example. The log
yeah,
to
so
the
if
fourth
you
will kill you then?
what?
The log to the fourth of d, that won't allow you to do 500. You have to do 500.
No, so this would be good. I mean, this would.
But even so, just the polylog, as you say, is a problem.
So if we use this one, so the result that is, I mean, improves the dependence on epsilon to the right one, we still have the log to the fourth d, which is, how much is that? I mean,
Well, log d is 16, so it's 2 to the 16th.
it's not 2 to the 16, it's 16 to the fourth.
16 to the fourth, right?
Yeah, that's pretty, I mean, okay. But, I mean, yeah, that's pretty grim. But
But also maybe conjecturally it might work with just log d, right?
Yeah.
yeah, all of this, it actually doesn't, it works without logs at all. Actually, just
So have
2
you
is
actually
fine.
tried experiments on your
I have.
your actual database to see how small k you can?
I have. These things work annoyingly well. I mean, you can barely make it break. If you can even use project. So let me say what this is, and then I'll tell you how annoyingly well it works. So What a thing we are facing in applications is people want to apply these random projections on very sparse vectors to begin with. So they have, let's say, some Word documents given in the bag of words model. So you just have the words in the documents or the accounts or whatever, and you want to project that. Suddenly, doing anything in the amount of time of the original space, O of D, becomes horrendous. It's the size of the whole dictionary. You actually want to do something in the size of the document, maybe 1,000 or 2,000 words. And actually, suddenly, those random Gaussian naive things in the beginning become much faster than all of this. So this is very annoying. I mean, maybe the sparse constructions also take advantage. I mean, it's slightly better for that. But this is it. This is what we know. We know that you can do sparse construction, but we don't know how to use anything fast for sparse vectors. Okay. And I'll tell you how annoyingly well it works, because so in Yahoo we use random projections, for example, for spam filtering. So you take inbound mail, you look at the mail as a bag of trigrams. So every 3 words is one word in the dictionary. So every document is a vector with maybe 1,000 non-zeros, but in dimension 10 to the 20. Every possible 3-word combination in all the languages that Yahoo receives mail in, which is all of them. Probably including Klingon. And you project them. So what happens is you project them down to dimension something like 10,000, and then just run a linear regression there. Okay? But clearly, you can't do anything of this sort when you project down from dimension 10 to the 25 to 10 to the 5th. Just anything, everything breaks. So what they do is just use hashing. Just you take your triplet, you give it a hash value between 1 and 10,000, and just add 1 to that location. It's not a random projection. It doesn't give you anything. I can prove to you in 2 lines that it breaks and that it's wrong. And it works beautifully. There's no constant, no logarithmic times, O of 1 pre-processing per non-zero. Everything you want works great. Shouldn't work at all, actually. And that's the way it is.
So, but aren't the random Gaussian projections used? Are they actually used in industry for these kind of purposes? I mean, they're extremely fast if you have very sparse vectors, right? If I tell you which location and which what is the value, if that's my representation for the vector, then it's extremely fast.
Yeah, so a slightly different. I mean, so usually you don't use the Gaussians, you use plus minus ones, and you don't actually use those. You actually use some hashing. I mean, you simulate your matrix by a hash function, because you actually don't want to store the matrix. You want to compute it on the fly. So, but yes, I mean that's.
In your original example, if I remember correctly, your data were images.
Right.
But the images are usually like JPEG, whatever. They're already compressed, so they're going to be both dense and fairly random. So presumably the Gauss projection of the random sparse matrices will work great.
Right. You can also subsample just. You can just subsample dense vectors, and that's already enough. I mean, yeah, I agree. The hard cases, in some sense, are the ones that are least likely, the ones that you actually never encounter in real life. So there is a big gap between what you expect to see and what you're trying to prepare yourself to. But then many of the statements become pretty trivial. I mean, if you can assume your data has been rotatedly in space randomly, then you don't need any of this. You just sample it. Just sample log n over epsilon squared entries, and that's it. That's a random projection.
But you really want not just your data, but the difference between almost
right,
duplicates. So
exactly.
That's not going to be randomly rotated.
I mean, yeah, if the entire data set is randomly rotated, then the differences are also randomly rotated.
But they're kind of, you get correlated images or something, presumably.
Yeah, I'm not saying I'm not saying it's a valid statement for images. It's probably not. But again, just having dense vectors and having dense vectors that have been uniformly rotated in space, et cetera, in practice seems to not really make any difference.
So out of all these different algorithms in practice, which one is the fastest?
Well, the hashing one.
No, but that wasn't in the talk. I mean,
That was in the talk. Oh, this one is the fastest because it's just, only one part of the, the rest also include that as a substep, so it's clearly faster, but they're all very fast. Yeah. Well, one of them I can't tell you. The one with the four-wise independent matrices, I can't tell you because I never coded it. I wanted to, but then it was too much work.